Welcome to The Explainer. Today, we're tracking a truly massive paradigm shift in computer hardware. We are going all the way from the microscopic, messy, physical flaws of your computer's processor, right up to unlocking absolute mathematical truth on-chain. It's a wild ride, so let's just dive right into this.
So think about this for a second. Is your computer actually calculating, or is it just guessing? It feels totally counterintuitive, right? We all share this grand computational illusion that our machines are just these flawless engines of pure undeniable logic. We just assume that when a computer does math, it's dealing in exact, rigorous certainties. But, well, we're going to shatter that illusion real quick today. What if I told you that beneath the surface, your computer is often just making a highly educated guess?
80 to 90%. Let that sink in. That is the staggering percentage of modern heavy compute cycles, and we're especially talking about the ones powering massive AI models and complex graphics. They're actually just hardware-level approximations. They are not calculating an exact mathematical truth. They're fundamentally just guessing the nearest answer that's literally burned right into the physical silicon.
To really wrap our heads around this, we need to pit two very different parts of a computer's brain against each other. In one corner, we have the floating point unit. Let's call him the FPU gambler. Now, he is incredibly fast, but he's lossy. He's probabilistic. He's basically throwing darts at a dartboard, just hoping to hit the right answer by rounding off decimals. But in the exact opposite corner, we've got the arithmetic logic unit, the ALU surveyor. The surveyor performs exact, verified integer arithmetic. You see, with the ALU, 1 plus 1 is exactly 2 every single time on every single machine on Earth. No guessing allowed.
Now, the consequence of relying on that FPU gambler is what researchers call the wood chipper effect. Because the FPU is constantly approximating and chopping off all those messy decimals, the exact mathematical path of that data, its provenance, is permanently destroyed. Think of it kind of like a giant digital blender. You might know exactly what fruits you tossed in at the start, but once it's blended, there is absolutely no way you can perfectly reverse engineer that smoothie back into the exact original apples and bananas. And look, while a tiny rounding error might be completely fine if you're just generating a funny picture of a cat, it becomes a massive systemic issue when we move into decentralized finance and blockchain networks, which brings us to what's known as the trig wall.
Section 1. Hitting the trig wall.
So here is the fundamental problem. Blockchains, by their very nature, require absolute, zero-tolerance agreement. Everyone has to agree. But the Ethereum virtual machine, the EVM, fundamentally cannot calculate floating-point math natively. If an on-chain smart contract tries to use our guessing FPU gambler to calculate continuous trigonometry, things like sines and cosines for liquidity curves, different machines will inevitably disagree on those tiny decimal approximations. And when that happens, boom! Consensus instantly shatters, the network forks, and literally billions of dollars are suddenly at risk. Forcing a blockchain to try and do this burns immense gas and leaves the entire system incredibly vulnerable to rounding exploits. So the really big question we have to answer is, how on earth do we do complex, curved math using only exact whole numbers so the network doesn't break? How do we fire the gambler and let the surveyor take over?
Section 2. The ALU surveyor takes over.
The breakthrough here comes through a seriously elegant mathematical evolution. Step 1, we completely ditch continuous trigonometric angles altogether. Step 2, we map that math onto Peele-Smith rational coordinates. And step 3, which is absolutely crucial, we strip out those insanely costly division and square root operations entirely. We just rip them out and replace them with simple, exact multiplication.
Okay, let's define exactly what's happening here. Peele-Smith coordinates are essentially a framework that perfectly replaces continuous, messy curves with an exact, pixelated grid of division-free integer math. You definitely don't need a math PhD to appreciate how brilliant this is. Basically, any integer solution corresponds to a perfect geometric rotation. It's clean, it is exact, and it is unbelievably cheap math that completely bypasses that EVM trig wall we just talked about. And this directly brings us to the macro-level impact of achieving this absolute mathematical truth on-chain. What does this actually mean for network speed?
Section 3. Flat O1 computational complexity.
Because we've removed all of those vulnerable heavy division operations, the entire state transition happens in one go. It's executed as a single matrix vector multiplication. That gives us flat, instant O1 computational complexity. There's no more expensive sequential curve crossing where the computer struggles and sweats to calculate a heavy path. The answer is just there, instantly. It's a total game changer. So let's move to the physical reality of this shift and see how this builds into just staggering metabolic efficiency for the hardware itself.
Section 4, the 74x energy floor.
Think about a standard 16-bit float operation. It's full of power-hungry guessworks, and it burns about 3.70 picojoules of energy. But when we look at the new 1-bit Pell-Smith ALU operation, which is running on that exact integer geometric rigor we just mapped out, it drops that energy use down to a hard physical floor of exactly 0.05 picojoules per operation.
Guys, that is a massive 74 times reduction in energy consumption. We aren't just talking about a marginal iterative software update here. We are talking about the absolute hyper-deflation of global compute costs, all because we finally stopped fighting the hardware and started speaking its native exact language. So we have blazing speed, and we have incredible energy efficiency. But how does this exactness actually secure the network against chaos and exploits?
Section 5. Achieving geometric lock-in.
It achieves what researchers call geometric lock-in. Because these coordinates are locked into specific predictable integer patterns, a chaotic path literally collapses and anchors itself into a stable period 2 attractor. Think of it kind of like a marble finally settling at the absolute bottom of a bowl. It can't go anywhere else. In plain English, the numerical drift is completely stopped cold. The machine is no longer guessing or approximating where liquidity is on a curve. It mathematically possesses the exact, unquestionable state of reality.
Now, the really crucial point is how this microscopic hardware truth connects to massive real-world business stakes. Right now, companies pay what the industry calls the mask rendering cost of narrative trust. Think of this as the endless, wildly expensive hidden tax of third-party audits, compliance delays, and massive legal fees, all just trying to prove that the system works and who owns what. But when trust is mathematically baked right into the exact silicon hardware of the ALU, that metabolic tax drops to near zero.
And this leads us to the ultimate macro-level impact here. We're talking hyper-deflation of compute costs. We're talking verified forensic accountability, because we can trace every single action backward with perfect symmetry. And perhaps most importantly, all that immense capital saved from skipping those grueling audits feeds directly back into building the network. This unlocks an era of extreme legal abundance and true exponential superlinear growth.
We've tracked this incredible journey today, from a messy, guessing microchip all the way up to flawless, deterministic global networks. By defeating the FPU gambler and relying entirely on the absolute truth of the ALU surveyor, we've essentially tricked rocks into thinking with lightning. So I want to leave you with this final provocative thought. Now that we finally possess absolute mathematical truth, what are you going to program it to do? Thanks for joining me for this explainer. Keep learning, and I'll catch you next time.